So this is all in chapter 5. I think it's chapter 5 of both books. I think. So one load per line, right? And then of course, if we need multiple loads, we put the loads in what we call this range right here, parallel. Yeah. So all we do is just keep adding lines. So how many lines can a run have? Can have many, right? You understand? A run can have many lines. We'll get y'all that in the next test. So here they got 3 devices. We're controlling this with a single pole, single throw switch. And then we got three loads, and they're hooked in what we call parallel, right? Okay. Of course, we know this is we call this line 1 and line 2. The book calls them L1 and L2, but this is going to vary depending on what application. Normally, they give these different names, but normally L1 and L2 will be in there somewhere. Okay. Of course, these are what we call overloads. So what happens with a motor? The motor draws a lot of current when it starts up. We call it starting current. Well, it's called rotor current. It's about 6 to 8 times, and it varies. Generically, if you don't know it, we assume that a motor will draw between 6 and 8 times its run current. So if I've got an overcurrent protection, what's it going to be rated at? Is it going to be rated at the motor's run current, or does it have to let the motor start? Got to let it start. So what happens if the motor stalls? Well, it's going to pull start current. Current protection by start current. And your motor stalls, it's going to burn the motor. It's going to sit there and just burn up, right? You understand? So what we have is we have these things called overloads, which looks for overcurrent over time. So what it does is lets the motor start, but if the motor stalls and don't start back up, it kicks these out. It kicks out your control circuit. And so these are what we call overloads. So these are the overloads. This would be for a single phase. This would be for a single phase where we have overloads in both lines. This would be for 3-phase, but very often now, most of your motor starters has one overload contact that's stripped by all 3 phases. So normally, this is the only thing, by the way, that's allowed on the L2 side. So normally, what we have on the L2 side is the load normally connects to L2. The only thing that's allowed between the load and the L2 are overload contacts. So if you ever see an overload contact, no matter what this is named, this is going to be a motor starter. It's a magnetic motor starter, which is a special relay that's designed to run motors that don't have overloads. A motor that does have an overload will use what we call a contactor. So this is a contactor. There's no overloads in it, right? You understand? This is a magnetic motor right here. I think I got my camera up. There it is right there, Rich. Just remember that. So this is magnetic. So this is a contactor. So it has no overloads on it. So this could run a motor, but this would only run a motor that's got internal. So this is a magnetic motor starter. Normally contactors, the difference between a contactor and a control relay is a contactor will have main power contact. So this is where your high current runs. And then somewhere it's going to have auxiliary contacts. So normally the auxiliary contact stays inside the control circuit, and then these will be inside the power circuit. Well, this is a motor starter. Can y'all see quite a bit difference? What do you think these are? These are overloads. So all the motor current runs through the overloads. If the motor comes in and pulls too much current, then it disconnects the control circuit. So this is a magnetic motor starter. This is a contactor. You understand the difference? The only thing that's allowed between L2 and the load is overloads. Everything else. So all the diagrams we look at are going to be like this. So here's the load. Here's L2. Here's the load. Here's L2. Here's the load. Here's L2. Nothing in here, right? You understand that? So this right here is probably what they call a control relay. What's the symbol for it? It gives you what's the load, and this is the call for a light. So right off the bat, if you see these contacts, these normally closed contacts over on this side, it means that this relay is a magnetic motor starter. That's the sensing element. The unit itself is an overload. So this is not a heater. This is the overload. The heaters, if they run heaters, the heaters are going to be out here on the motors. So we'll come through and we'll have contacts if it's three-phase, and then we'll come through and have this thing right here. Now this is the symbol. This is the symbol for the heaters. That is not the symbol for a heater. This is a symbol for an overload contact. So the heaters control the contact. So if these guys sense too much heat, they open up the contact. And we'll look and see how that happens. So this is the heater. That's the what? The contact. That makes sense. So these would be heater. We see a lot of heaters used for overloads. We'll get there because they're cheap. And most of your new motor starters are going to use electronic overloads. Everybody okay here? So control devices go where? Control devices go between L1 and the load. And then on the other side, this connects directly to L2 unless it's a motor starter, magnetic motor starter. It's a parallel circuit. What makes a circuit a parallel circuit or a series circuit is not the way you connect the control devices, it's how you connect the load. This is a series circuit. It's a single. If I get my voice, what's nice about motor controls is that series circuits are only going to be one load circuit. We're not going to have multiple loads. This is a series circuit. This is the load right here. This is what makes it a series circuit right here. Not this. It's not how you connect the control devices. It's how you connect the what? Load. So this is a series. This is still a series circuit, not because of these. But I could come in here very easily and so I could come in here very easily and come up and do this. And now this is a parallel circuit, right? You understand that? Well, these are connected in series. It don't make any difference. Those are control devices. Control devices do not determine if it's a series circuit or a parallel circuit. It's how we connect the loads. What's nice about motor controls is that's illegal. So that's a series circuit, but it's illegal, right? You understand? How many loads per line? One. Everybody okay on line numbers? Yes or no? So every horizontal line gets a number. Everybody understand numerical cross reference numbers. So I look at this number right here. What do I know? I know. So here's CR3. I know there's a CR3 contact in line number what? 7. So here's line 7. So I'm going to come up here and start looking at line 7. Line 7 comes across. I need to do that. Here's CR3. I'm sorry. CR3, and there's that contact. I've also got a contact where? In line 9. I'll do it in a different color than black. So here's line 9, CR3. There's the contact controlled by that relay. I've also got a contact in line 11. I come down here to line 11, and there's the contact controlled by that relay. Everybody okay? Light bulbs don't have contacts. How many in this class is going to put numbers out here beside a light bulb? Somebody in this class is going to do that. I don't understand why. They'll try to put all the numbers up here for some reason. They'll put numbers out here beside light bulbs. Light bulbs don't have contacts. They are not coils, they're lights, right? You understand? Who's going to do that in this class? Yeah, I wish. I wish. If it happens, we'll celebrate because I've never taught a class yet that somebody didn't do that. What are we looking for here? So this is, I know this is a magnetic motor starter. Why do I know it's a magnetic motor starter? Because it's got overload contacts, right? You understand? So this is the only thing that's allowed right here on between the load and L2. Well, right here it says I'm looking for a normally closed contact in line what? 13. And there it is right there. Everybody okay? Yes or no? It's going to have the same name as the relay. So don't jump on the M as being a motor starter. That's just the name that the book uses. It could be what? It could be any name. It's up to the company. The company is the one that's naming the relays, whoever designs the thing. Did I still have my U.S. Steel print up there? No. It's not graphics. I think it's an handout. So you can have a copy on this, and eventually we're going to have to start asking about this guy if it ever comes up. So do you see any relays on here labeled M? No. But they're given names according to what they do. Of course, over a while, you would pick up, so 5B, number 5 bridle, number 1 braking, dynamic braking relay. So after a while, once you work on this, you'd pick up these names, right? You understand? But what they do is they give this what we call a mnemonic, which is a memory jogger. And then now I know any contact that belongs to this relay will have the same name. And that's also true in PLCs. So PLCs, if you take PLCs, you assign a contact and address, but you'll learn real fast you need to start assigning those things names, right? You understand? And it makes it real easy to figure out if you can see those names. By the way, people always ask me which is easier to take first. It don't make any difference. If you take motor control first, it makes PLCs easier. If you take PLCs first, it makes motor controls easier. The difference is motor controls deals with what over here they deal with rung numbers. And then PLCs, and motor controls deals with line numbers. Big difference. So the book, what the book will do is the book will call your motor starters. They're going to give them all the name what? M. M1, M2, M3, 3, or 4. Your control relays. Now, what's a control relay? No, a control relay will never control a motor. So what we're trying to do is we're trying to see what controls the motor. We call this a control diagram, or we call it a line diagram. A control relay's contacts are only used within the line diagram. They never leave. There never will be in a power diagram. So normally what we do is we have two different drawings. We have a control diagram, and then we have a power diagram. The power section is usually going to be a high voltage. The control is going to be a low voltage, right? You understand? That's why we want high voltage to run power. It is more dangerous, but that's not okay. So that's not why we want to use high voltage in our power section. What do you mean by bad reference? Yeah, well, I is equal to P over V. Well, what am I trying to say? What's this motor rated at? Well, this motor's rated at 30, might be rated at 30 horsepower. Now, over here we use horsepower. We're still using horsepower. You know what that means? Well, roughly it's 246 watts per horsepower. So if I've got a 30 horsepower motor, it would try to do what? So I'm going to say 30. So watts would be equal to 30 times 746. What would that give me? What's that? So we would say 2, and then we'd say kilowatts. Okay, you understand that? Is that okay? Okay, let's say I'm going to run this 2.2 kilowatts, and I'm going to run it on 120 volts. So I would be equal, and so the motor's rated at 120 volts, so it's going to be 2.2 K divided by 120. How much current would that be? 186 amps. Let's say I run it on 440. So my motor is designed around 440. So I'm going to say 2.2 kilowatts divided by 440. What would my current be? Really, it'd be just 186 amps. Everybody get that? I didn't do it right. Okay, that probably makes more sense. 8.3 amps, right? And what's it down here? 440. Now we're back in the milliamps, right? Everybody get 5 milliamps? Okay, so which one would require the biggest wire? Which would require the bigger relays? Okay, so this means I need bigger wire, right? I need bigger relays. Down here I can use what? Smaller gauge wire, smaller control devices. Okay. Now how much is it going to cost me to run? Well, it's going to cost me this right here to run. So people say high voltage is more efficient. That's not more efficient. You pay for watts. Y'all understand that? It's just that when I run it, when I install it, it's cheaper to install. It's easier to install if we run it on what? High voltage. So your high horsepower motors are probably going to run at a higher voltage, but they're designed around that load. What if I came over here and had a motor that was designed around 120 volts and I tried to run it on 440? Burn up as soon as you hit it. Because 120, 440, that's 4 times. That means it would pull 16 times the power. So your loads are going to be designed around a certain voltage. And if you need to run them at that voltage. So at your house, your high wattage devices are designed around what? 240. Is it cheaper to run that way? No, they're watts, you know. Y'all understand that? So you look, all these devices are rated at a certain watt. It's just that the higher they run it, now we can run smaller gauge wire, which makes it cheaper and also makes the wire more flexible, easier to pull, easier to run, right? You understand that? So it's cheaper to install. I mean, US Steel had some, I think the blower motors on the Q-Bops are like 3,000 horsepower motors. You think they ran those on 440? No. They ran those on like, I think 6,000 volts because you just couldn't run wire this big out there to run those motors, right? You understand that? So a control device, so that means a contactor are going to have, a contactor and a motor starter are going to have contacts in the what? In the power circuit. A control relay, the contacts are never going to be in the power circuit. They're going to stay in the what? They're going to stay in the control circuit. Everybody understand that? I should have done this one. I'm recording this. So this is a control relay, and they're called control relays because they stay in the contacts or in the what? The control circuit. This is a motor starter, so not only is it might have contacts in the control circuit, these are going to be auxiliary contacts. It's also going to have contacts where? In the power circuit. So our control relay is going to be a little, we call them peanut relays. Of course, they all vary depending on what. So this is our control relay right here. Would you run a motor with that? No, I don't think so. These are what we call, what are these called? These are called wire numbers. Everybody okay with wire numbers? So I'm out there trying to wire. Now cars don't use wire numbers. They color code the wires. Have you ever got in that? So every wire's got a different color. You use stripes and all kind of neat little colors on your car. So have you ever looked at the wire harness in a car? Motor controls, normally all this wire would be the same color. So how do I differentiate the wires? We differentiate the wires with the sign and numbers. Normally we start in the upper left-hand corner and we start number wires. I understand that. The control diagram. Why does this one not get wired? Why don't that one get a number? Because any wire that's electrically the same is the same number. Y'all understand that? So that means if I came over here and I put a voltmeter from here to here, I would measure exactly the same. Okay, that ain't going to work, Rich. That's going to measure zero. Normally when we measure inside a control diagram, normally what we do is and this is why you got those alligator clips with your meter. Normally what we do is we come up, and this is the safest way to do it, is to take your one of your leads and put it right here, clip it onto that, and then we make all our measurements relative to this point right here. And that way you're probing with how many leads. You don't like to probe in a circuit with two leads. And why is that? Yeah, you have to use both hands. Of course, one of the most dangerous tasks is most dangerous. Here. Right. It takes it through your wallet. Here's low resistance. This is one of the least resistance tasks. The skin is so thin up in here. So this is a pretty good task because your hands have pretty good resistance. But you learn all that do, even troubleshooting most circuits, is we make our measurements relative to the common of the circuit. So that means if I took a voltmeter and then I measured right here, this and this are exactly electrically the same. They're connected together. So it means this does not get another number from that. So notice on these, all these line numbers down here, these are all what? They're 1 because they're all L1. They're all L1. So that means if I wanted to measure between here and L1, all I got to do is find a wire that's got what on it? The 1. So anything that is electrically the same that does not go through something gets the same number. As soon as I go through a device, it does what? Changes numbers. Now, why don't we have a number down here? It's electrically the same as that. So if I wanted to measure across this contact right here, all I got to do is I can find 1 to 5. 1 to 5 is across that contact no matter where it's at, right? You understand that? So everything that's electric, everything that's connected together gets the same number. Every time you go through something, it gets a what? Another number. Are you okay? These are what we call manufacturer numbers. We're going to do this a lot. So when you buy a relay or anything like that, it's going to have, it's got contacts to it. It's going to have numbers on it. How did these numbers get on here? Well, these were assigned by the manufacturer. So these are the numbers right here. These have numbers here. What they've done on our trainers, they've transposed the numbers up here to these banana plugs. Wrong side of it. So this would be L1, L2, L3 got wiped out. This would be 5, 7, 2, 9. This down here would be what? T1, T2, T3, 6, 8, 3, 10. Okay, does that make sense? So then what you'd get is you'd get a little paper that comes along with it that shows you the actual assignment of the pins, where the pins are actually electrically assigned. I pulled it all the way out a while ago and I can't get it out. So this is the little diagram that would come with the sheet that shows you these different assignments. Well, so here's my power contacts over here. This is where the motor would actually be connected. Here's my auxiliary contacts right here. So y'all can't see this number right here, but this is number 6. So if I want to use this contact right here, I would use number 5 and number 6. Y'all understand? Who assigned these numbers? The manufacturer. So they're called what? Manufacturer numbers. So this is one of the first things I'm going to require of you before you hook things up, before you hook up anything. What's the first thing you're going to do? You're going to come on your diagram and you're going to put the manufacturer numbers that you're going to use. And you're not trying to look at two things at the same time. Now you're looking at the control diagram and you say, okay, you need to put this number 4 on the stop button. You need to put this number 6 on this and that. Now you have to understand these are numbers. What these are files, these are different buses all over the place. So you can't say, oh, this is number 6 because there's going to be 4 number 6s up there, right? You understand? But you're going to say, okay, you're going to get the number 6 on the stop button. You're going to get the number 6 on the relay. You don't understand that? So we have that happen every time. They'll see the number 6, they'll look it up to the first number 6 that's up there. And so everybody okay with manufacturer numbers? So all our parts have the manufacturer numbers on them. That's the first thing you're going to do before you hook it up is to do what? Assign them. Actually write them just like they are already. This, anytime you see a dash line indicates they're mechanically connected together. Sometimes when we assign this, the two devices that are mechanically connected together can't be put in consecutive rungs. So what they'll do is they'll put this little old house right here. Y'all see that thing right there? This means there's a mechanical connection, but it's not in the next rung or the next line. So the dash line up there indicates those are they're mechanically connected. They're inside the same unit. They're controlled by the same operator. Okay, you understand that? So what does this tell us? That tells us this is mechanically connected to something in line 1, 5. This tells me it's mechanically connected to something in what? Line 1. So that means there's a mechanical connection. When they came up with the drawing and they tried to do the logic on basically the sequence of things happening, then normally sometimes these devices that are mechanically connected can be, we can't draw those dash lines. Basically, this is the basic layout of a rung. We start off with what? Signal section. Normally, when I learned it, I didn't learn this. I learned there was 2 sections. That was the decision section, and then that was the action section. The book teaches 3 sections. They teach one for sensors. So what's a sensor? So we don't have sensors. Well, sensors are a device that takes a physical quantity and converts it over to electrical. So a flow switch. So what is a flow switch going to be? Well, it's going to be out there in flow. And then it's a certain way, it's going to close the contact. And that's what they're talking about here. These are your signal section. Temperature switches, pressure switches, flow switches, light switches, all these different types of things. Not light switches like that, thermoelectric sensors that we have a lot of. That's what they're calling the signal section. So these are sensor sections. Then we have the relay contact section, right? And this is where we can do memory, we can do logic, and then we have the action section. So these are going to be where your relay or your solenoids are, right? Basically, it's decision, action. So the decision determines when the action takes place. But the book added that second section, that third section in there. Okay, now take a break. 10 minutes, right? And now listen up. So logic. Everybody okay with logic? Ands, ors, nots, mans, nors. How many do we need to get an and? You got to have at least 2. How many can you have in an and? A lot. Y'all understand that? A lot. Not as many as you want, but as many as you need, right? Minimum of 2. Minimum of 2 to get an and. So normally open contacts in series, whether they're push buttons or contacts. So I could come up here and do this. So these would be contacts, right? And then this right here would be, that right there would be an and. So you'd say, if I call this A, B, C, and D, you basically say it, you'd say, well, A and B and C and D would have to be closed to make this thing work. Or anytime you use the term that right there, that's saying all those contacts have to be closed. So if you hear that term in your head, well, all those contacts got to be closed, and that means it's what? And. This is an OR. This could be done contact-wise. We could have Yeah, or if you use this term right there, any, or you say A or B or C. This is one rung, by the way, because you don't see that. It's one circuit. So, by the way, you need to put the dots, right? If you don't have the dots, you don't have a connection. You'll understand that. You can combine logic. So, these contacts right here, watch this symbol. Pressure switch, flow switch. These are hooked in AND. These are hooked in OR. So you can have different logic in the same rung. Yeah, so when we get to NAND and ORs, that's what gets people confused. So people think that they're in parallel, they're some type of OR. If they're in series, they're some type of AND, and that's not true. We got four logics we can do. One of the four different types of logic we can do. Yeah, we got AND, we got OR, then we got NAND, and we got NOR, and we got NOT, and that's it. And then we got exclusive ORs and exclusive NORs, but those are special, which we'll look at in a second. These are the five basic logic functions. So these right here are hooked in AND. These right here are hooked in what? OR. But don't look at parallel being. So a lot of people think that ANDs and NANDs are going to be in series. That's not true. So here the contacts are in series. Here the contacts are in parallel. So don't get that in your mind that if it's in series, it's an AND. If they're parallel, it's an OR or NOR, and that's what gets people in trouble. So yeah, they're normally open, and parallel is an OR. Normally open in series is an AND. Understand that? So we're fixing to swap this up. But the term is what you're looking for. If this pops in your head, this means this is what? This is going to be an or NOR. If this pops in your head, then this is going to be a what? It's going to be an AND or it's going to be a NAND. And that's the trick right there. Once you learn that little trick, then whether in series or parallel, that make a difference. So this, when we get into, so this ANDs and ORs. So this is the load, right? You understand. So ANDs and ORs are what's required to turn the load on or energize. So that means to turn this load on, this and this has to be closed, and this or this has to be closed, right? And then that load would turn on. It's a lot easier to see if this was a light bulb. So it means to light that bulb, this and this has to be closed, this or this has to be closed, and then the light bulb will come on. Well, what's required here? Well, this is a NOT. So NOTs, NANDs, and NORs turn the load off. They're just opposite from each other. So notice what happened. This is a normally closed, normally current contact push button. So when I put power on L1 and L2, this light is going to be lit, and this solenoid is going to be energized. What happens when I push the button? The light goes out, okay, and the solenoid is no longer energized. Well, okay, so NORs, NOTs, and NANDs are what's required to turn the load off. And the ORs turn it on. So what is this? Well, a lot of people say, what's an AND? They're in series. This is not an AND. This is so any of these will turn the load, what? Off. Any. So when I say any, it's either an and or it's a nor. Here, any load turns it off. So what's this? That's a nor. But the problem is people will jump on, if they're in series, it's an and then they don't pay attention to the logic. So ands and overs turn the load on, not and and overs turn the load what? Off. Here I said what? Any of those push buttons will turn it off. If I use the term any, it's either going to be an or, a no or what? Normally closing series is a or. Well, look at this. What's required to turn the load off? So you see normally closed contacts, NANDs, not throwers. Open contacts are going to be what? Or drains. These are normally closed contacts. What's required to turn the load off? All those have to be what? Open. So this would be a what? A NAND. And I could string these on a long time. Right, normally closed. Now look, every time in the book, if they have a connection, they put a what? A dot. So if you leave those dots off, what does that mean to me? So what am I going to do? I'm going to put like a -2 or something like that. Auxiliary contacts are added to give circuits with push buttons memory. So this guy right here has 2 auxiliary contacts. Where was that? So notice, let me zoom out. Well, they don't have to normally be on the side. Normally, we call our 3-phase, we call them L1, L2, L3. So here's your power contacts, L1, L2, L3. Then I got this contact right here labeled 2, 3. That's an auxiliary contact that's built into the relay. So these are your power contacts right here. These are auxiliary contacts. Now this comes in this relay block when you buy it. So if you buy this part number for this relay, you get 3 power contacts and 1 auxiliary contact. And then you have the ability to add another auxiliary contact, which is over here on the side. So, by the way, most of your relays have what we call an override or manual operated or push to test. Be real careful when you do this. This could kill people. So know the effect of what's going to happen when you force this contact. Can you see me forcing it? Now, what happens if you see this auxiliary contact, normally these are screws. They've got this braided on here. But notice you can actually see the operator operate on the side. I don't know if y'all can't. If I pass it around, you can. It's the same color. Can y'all see it move? So that means I could take another auxiliary contact and put it on here, and it would operate off this thing right here. Okay. Here's the operator coming off to the side. So this is what the auxiliary contact would pick up on, is this operator right here. Can y'all see it? So this has 2 auxiliary contacts on it. It's got 1 built in, and then it's got 1 on the side. So here's your power contacts right here. These will be in your power circuit. Your auxiliary contacts are going to be in your control circuit. This is a contactor. This guy here only has 3 power circuits. And notice this is for 3-phase, L1, L2, L3. But on the side, it's got what? These are auxiliary contacts. This one, but you can see the operator. It's got screw holes right here, so I could do what? I could buy another auxiliary contact and put it on here. And then when I operate it, you can actually see it would cause the contacts to either open or close, depending on whether they're normally open or normally closed. Are you okay? So auxiliary contacts allows us to have a contactor or a motor starter. These contacts are for the power circuit, then your auxiliary contacts will be part of the control circuit. Okay, y'all understand that? So here we got a motor starter, magnetic motor starter. So that means somewhere in its all overload, so it's probably three-phase, we have a power circuit. So the three-phase motors are going to be out here. This is called M1, so these right here would be labeled M1. By the way, let me draw a little more too. Then what we'd have out here is we would have the sensor for our overloads. That's the symbol for the sensor. That actually senses when the motor's got an overload. Up here, these are going to be called L1. Your three-phase are normally called L1, L2, and L3. And that by here on the relay side, this is normally called T1, T2, and T3. Huh? Yeah, thank you. But look, so how does this work? This is what we call a memory circuit. It's also called a three-wire circuit. Is that we have a stop button. The stop button is hooked in a what situation? What logic? No, what logic? It's only one of them, guys. Huh? What? Not. It's only one of them. You can't have an all when you only got one of them, right? You understand? So that's a not. We have a push button, and by the way, the book does a very poor job. This should be up here a lot higher. These are hooked in what? Logic. Or, good. You're right, they're parallel, but we're looking for logic. Okay. So how's this going to work? So I'm going to come up here, nothing, I can sit here all day long and push the stop button, nothing's going to happen, right? But as soon as I come over here and press this start button, what's going to happen? It's going to energize M1. M1 says I have a contact in what? Line 2. I'll look at line 2. There it is. So what's going to happen? It's going to close. Now what can you do with the start button? You can let it go. Now this thing is sealed in. How long is it going to be sealed in? Well, two things are unsealed. One is power fails. And this is why this circuit is so popular, because it's safe. So if I had a switch out here and I had a motor running and I flipped that motor on, your power failed, the motor would stop. When power come back on, what will the motor do? It'll take off, right? No matter if I'm out there looking at it or working. If this guy here, if the power fails, we lose L1, L2, this guy here drops out. Now when power comes back on, the operator has got to deliberately do what? Push the start button. So this is why most companies use this memory circuit to run motors. So that way if power fails, when the power comes back on, it's not going to do what? That motor's not going to take off. But the normal way we do it is just do what? Push stop button. As soon as I push the stop button, we lose our current path. The relay drops out. This contact right here opens and it sits there. And so this is called a seal-in circuit. It's also called a what? Memory circuit. And this diagram, by the way, is called a three-wire. So anytime we have something that runs and we don't have the control that runs like this, then this is what we call a two-wire diagram. As soon as I add the seal in, then we refer to these as three wires. So this thing got three different names. It's called a memory circuit. It's called a what? Seal-in circuit. It's called a three-wire circuit. All those are interchangeable. But this would be auxiliary contacts. Out here in your power circuit, I'm not going to draw the overloads, guys, sensors. Out here in my power circuit, I would have the power contacts, right? You understand? So this might be L1. This is labeled L1. Down here, this would be labeled what? T1. Up here, this would be labeled what? L2. Down here, it's going to be labeled T2. Now up here, this would be called L3, and down here, this is going to be labeled T3. But the name of the contacts are going to be M1. These are going to be your manufacturer numbers. So I could look at the the magnetic motor starter. So here they are. These are the manufacturer numbers: L1, L2, L3. So my lines would come in on this side, and then my motor would hook up where? Oops, hooked it the wrong way. No, that's right for y'all. Yeah. Nope. Oh, okay. And these right here would have numbers, and they've got numbers on them. I don't know if y'all can see them or not. That were assigned by the manufacturer. Y'all can't see it. This is there's a normally open down here. That's normally closed. That's 21. This is what, 13. Can y'all see the manufacturer numbers right here? I know it's hard to see. I can see the numbers. Right. By the way, this whole circuit is sometimes called a start-stop circuit. But you don't have to use it to start a motor. You can use it to energize everything else on your control circuit too. Usually an e-stop button is somewhere down this line right here. So we can change this to an e-stop button. We could come over there and this could be emergency stop. So I could take out the overload, maybe call this E-stop or something. And then right here in L2 we would put an ES contact. That makes sense. And then I could come over and hook how many stop buttons could I put in series? Well, at least one. It's a not. Now we've changed it into an and, right? You understand that? And by the way, E-stop buttons have to latch. So that means if I hit that thing down, this thing here latches down like this, and you can come up here and you can do what? You can be on the start button all day long. You literally have to go back and unlatch E-stop buttons. So our E-stop button up here does that. So when you hit it in, what do you have to do? Now, most of your newer E-stop buttons, you don't just pull them back out. You got to do what? You got to turn them suckers. So this is a typical E-stop button. So your sealing circuit does not have to run a motor. It can actually run an E-stop. And that's what happens. I kill the what? I kill L2 with the standard E-stop button. Two push buttons paired in parallel. So this would be where we can come in and we can start a motor from different locations. This does not tell you where they're at. This is the logic, right? You understand? If this was a wiring diagram, we might have one drawn over here, one drawn over there. It's very common to have multiple stop buttons and multiple start buttons on a motor. Very common. Because it would be awful if I'm going down here and I need to start the motor from down here, and I got to walk all the way back up here to start the motor so I can come back down there. So multiple stop buttons and multiple start buttons are very, very common. So this is why I like it. Or these are, they're not at two. I got two. If it's a knot, there's only to be one. If it's not an or. I'm sorry, just trying to get it right. I say E, so this is a one. No, somebody said it right. If you said no, you were exactly right. Yeah, so as soon as I see more than one, then it's not a knot anymore, right? Understand? Watch this right here. That's a knot, because there's how many of them? One. This is a two start-stop station controlled by one stop button. This is very common. Okay here. So we got an E-stop button. Stop both of them, and then we got a stop button on each line. Okay. That's not the right symbol for an E-stop button. An E-stop button, this usually means a push button operator. Most E-stop buttons have a mushroom operator, so it should be drawn like that. Two motors can be started almost simultaneously from one location. Notice here we have would this be a power contact or would this be a auxiliary contact? It'd be auxiliary. This is not the motor. This is the coil that runs the motor, right? You understand that? So this is nothing but a relay. So that would be an auxiliary contact. Are you okay here? Yes or no? Pilot lights, we love pilot lights. You'll see how pilot lights are very easy to connect. Normally you just connect them in parallel. Not logic is used to indicate the device. And we're going through the whole lecture. We don't need to do that. This is all in the lecture, right? So what y'all need to do is let me know if y'all got any questions about this because we need to do some labs. A sequence control. What is a sequence control? Yeah, so notice I can't start M2 unless what? M1 is running. A selector switch. So this is what, by the way, we got different names. Anybody know what when you talk about motors? Yeah, but what plugging means is when we reverse the direction of the motor without it coming to a stop. So that's plugging the motor. Okay, that's jogging. All the time, what's jogging? You bump the motor, move the motor, try to position something. Well, normally what we have to do is we switch. Once we get it where we want to, we can run the motor. How do we do that? Well, we just break the memory circuit, right? Understand that? That makes sense. So here we got selector switch. Now, selector switch, once you put it into a position, it's going to stay in the here's the selector switch. So the only switches that you see in motor controls are selector switches. What we call a three-position selector switch. So notice what they do right here. This is a two-position selector switch. Notice how they do that. So when we're in this position, this solid line is closed. When we switch it to this position, see the dash? It means this is going to open, and this right here is going to close. Well, this bottom one is not connected to anything. So that means if I switch it over here to this position right there, then when I press the button, this contact's going to close, but this circuit down here, we don't have a seal in anymore, right? You understand? So I can hit the run, and jog the motor. If I put it on to here and then hit the start, then it's going to seal in. So this is a run jog circuit. Two-position selector switch. By the way, these are going to be called legends. So normally what they do on these switches is they put a little tag on the switch that says what it does in that application. Have a little tag on the switch that says run and jog. See what the selector switch looks like. I can just take it off here. It's not going to be on the air cord. It's up here on the panel. Let me just take this off here. But you don't want these. So what they do on these, just to give you a feel of what it would be out in the field. In the Navy, we used to call it the fleet. So we were going through all our schools in the Navy. Let's say when you get out in the fleet, when you get out in the fleet. So up here we'll say when you get out in the field, all your buttons and everything should be what? They should be labeled. So this is called a legend plate. And basically, when they're just got a hole cut in it that's the same size as the mount, and you just slide them on it. And you can buy this type of a thing. It's basically got a color on it, and then it's got a white centerpiece, and then they just mill out these different signs, which is pretty neat. Now, so they're calling this light what here? They're calling it stop. They're calling this light what? Start. And they're saying, okay, this is a 3-position selector switch. So a selector switch stays in the position you should leave it. But when you need a light bulb, you don't have to say, well, I can't use that when it's labeled stop. It's a light bulb, folks. So in this class, it don't make any difference what they say. If you need a normally open push button or a selector switch, it might say manual and auto, but you can say, well, I'm going to use this for run and I'm going to use this for jog, right? You understand? So these legend plates are in there just to show you an example of what these switches could be used for. It doesn't mean you got to use them for that feature, right? So if you need a light bulb, you use these guys right here, right? Everybody okay? Now here's the manufacturer's numbers right here. And of course, this shows you the actual schematic. This is the selector switch for symbol. Have you already got one out there y'all looking at? Okay, good. So this is the way we troubleshoot, guys. So what we do, we're dealing with 120 volts AC in this class. That's going to be our control voltage. We're going to run to a transformer. We're going to start off with 208 or 15. We're going to run it into a transformer that you're going to wire to divide by 2. Okay. And that means we're going to roughly 108, 115 around there volts out there on power. So normally what we do when we troubleshoot this is we take our black lead, we're looking for volts, right? You understand that? So what we're going to do is we're going to take our lead. Now here they're showing the black lead. I mean, you got to use the black lead, AC. Don't know AC has no polarity, right? So if you count red, if you're doing DC, then you got to put your black lead over on L2. You need to. You know, we analog meters, and if you look in something backwards, you can mess up your scale. So they have a little wire in between, going in one direction. So what you did is you look at the positive voltage, you use your black lead for your common. If you're looking at negative voltages, you had to use your what? Your red lead for your common. Your digital meter over here. It's just that if you use the red lead for your common, and you use a black, and you measure with your black lead, your voltages are going to be the same. It's just that they're going to be what? They're going to measure negative. That's no big deal, right? If you understand that. In fact, I'll do that a lot in DC. You learn to measure the series circuit. And people would take major leads and they keep going like that. Well, if you ever watch me, I go like this and like that. I don't move one lead. And it makes measurement like that. Just don't write down negative. Don't do positive. AC makes no difference. Black lead makes no difference whatsoever. So here they're showing black lead over here. Look how they're making this DC. It doesn't make any difference. And then what do? So let's say this thing's not working. What do? Well, you start over here. Well, first of all, what's the basic steps? What's the number one step for troubleshooting? So the number one step for troubleshooting is understand how the system's supposed to work. Number one. If you don't know what it's supposed to work, you can't troubleshoot it. Right? You gotta know how it works. What's number two? Clarify the problem. How many people still troubleshooting out there and you gotta say this thing don't work and you gotta have a switch if you have a switch out of it. verify the problem. It's not working at all. If it's not working at all, you can verify the power source. If it's working somewhat, then the power source is probably okay. Okay. Verify power. Number 4, you look things over. Just look things over. Right. And then 5, you actually start to troubleshoot. You start to trigger. Normally what we do is we troubleshoot from common out. And this is also true in electronics, guys. So this is kind of misleading. I would actually put my blank. So this guy is not working at all. I sit here and press the button. Doesn't work so well at all. I verified the problem. I made sure I had one. Power on L1, L2. Pretty easy to do. What is it not? What's the first thing you do when you go to the doctor? First thing they check is your power supply, right? So they check out blood pressure. Blood pressure, and they call my son. Boy, my son drives motor retro. So he says he sees dead people. They miss one spot. I'll start here. I'll go right here, check the overloads. How much voltage should the overload drop? Nothing, right? Yeah. So this overloads are open. And I'll go on. Go right here. By the way, when you go right here, you're going to have 2 people because you got to actuate these buttons, right? You understand that? So come over here, have somebody do what? Push the button. If it goes up to 120 volts and nothing happens, it probably means the relay coil's bad. Okay, well, I get nothing more. I go next. I go right here. Right, you understand? Now, right now, if I measure 0 volts, I know it's got to be one of these guys. Go right here, measure 120 volts. That guy's bad. Right, you understand that? Pretty simple. So normally when we troubleshoot these things, we troubleshoot, and this is what bothers me, is that these circuits are extremely easy to troubleshoot. And by the way, I'm doing lab, and I get over there and got a problem. If I call a class over there, don't get upset because we're going to learn here. It really bothers me when somebody does a circuit and it don't work. We tear it down and we learn. It don't work. So tear it down and retry. When we find out, we can probably figure out what's wrong with it. Probably 30 seconds. It might take you 30 or 40 minutes to require circuit. Oh, you got one wire wrong. So, if you got it wrong, then that's a good opportunity to do it. You'll be surprised how many, especially in new installations, a lot of your problems is just something wire wrong. With magnet most starters, DMA2, a good mechanical switch should drop. So how much voltage should a push button drop or a mechanical switch drop? Nothing. Solid state, usually around 2 volts. So solid state sensors actually drop a voltage. So we'll talk about that when we get into sensors and transducers. Okay, guys, what we're going to try to do is we're going to try to do a lab. And what's the first lab we're going to do? No. First lab we're going to do is, there's 3 labs. They're going to be homework labs. I guess I'll hold that. Yeah, so first lab we're going to do is safety. Let's go ahead and do that. Let's be turned in Thursday. Just click on that. I think it's first. I think we have another lab. One. There's 3 labs. More labs. Lab 1 is, I guess it's lab 1. safety, uh, these are all hard to first do Thursday. They're all safety. All of y'all need to pay attention. We already talked about this. Where's our fire extinguisher at? Where's our safety kit? Where's our first aid kit at? By the way, on some of these are going to ask you to measure wall outlet. And for some reason, people don't understand they got wall outlets at their house. So you don't have to come here and measure one of my wall outlets. You can do what? What's that? Another lab book? Yeah. By the way, y'all see the way the lab book's set up, right? It's set up in chapters. So you got a chapter called the S chapter. Okay, see that? Then you got 3 labs inside that chapter. What's at the end of the chapter? That quiz. Let's see what it is. I need to explain for each of y'all a little further because we're fixing to what we're fixing to do is systems familiarization, SF1. That's what we're going to do today. So what we're going to do, what I want to turn in Thursday is inside the safety chapter, which we'll call the S chapter. I want you to do homework. I want you to do lab 1 and lab 2, experiment 1 and 2. Okay? Everybody okay? All right, I'll put that up on the calendar so we can do. So some people that's not here. What we're going to do today is we're going to do system familiarization, which is the system section of the lab book, which is the SF section. Okay, y'all listen. Y'all listen. This is where we're going to inventory our trainers. This is where you're going to take your partner. So somebody can work with yourself today. That's what y'all. We need 1, 2, 3, 4, 5, 6. Starts on essay and the essay. There's no page numbers. There's no page number. Actually, there's page numbers. There's page numbers reference to the lab. So if you look at the numbers, page numbers will start with essay. It's going to be the chapter. That's system familiarization. We're going to do lab 1, which means we're going to inventory our kits. Now, all our parts are NEMA parts. You know what NEMA stands for? National Electrical Manufacturers Association. We also have ICE parts, which is the International Consortium of Electronics. We have all the NEMA parts here. We've got pictures in there. So what you're more concerned with is the name. So every module has a name on it. Everybody okay? You didn't get a lot. Okay. I'll have to find them. Oh, they are. Look, they're there. So y'all understand the way the lab book's laid out? Are you okay? So what are we going to do today? Step 1. Right. It is inventory. Okay. Now what I have to help you out is I have an inventory sheet up here that we're going to find these parts. I'm going to put this part on here. And then we'll attach this to the lab when you turn it in. Everybody okay? Everything. chapter or section, but the first page of the lab has to be turned in. Okay, you understand that? And what I want you to do is not turn in the lab today. I want to make sure y'all do this right. Keep up with your time. We keep up with the time on our lab. Okay. So what I want to do is take these parts off. Instead of marking them off in your book, I want you to mark them off on this sheet of paper. Okay. By the way, we have station numbers. Can y'all see the station numbers in the upper right over there? So there's station 1, station 2. Don't use station 1. Most of the parts have been marked off. So let's start down this side. Yeah, no, each person is going to have one. So everybody turns in. So I know it's going to duplicate a lot of stuff, but you're responsible for your lab. We don't turn these labs in as a team. We turn them in as an individual, right? You understand that? You're responsible for your paperwork. You're not responsible for your partner's paperwork. Yes, sir. I just thought. So here's our 2 boxes right here. It says what? It says labs not ready to be graded. Yeah, here's all the platforms are in. Well, we'll keep this added. We'll keep this up on the total record. Hold on here. Hold on. So you have any questions? Yes, no. Somebody leave. Probably went to get his lab book. Okay. So by the way, let me tell y'all what we're going to do. These circuits are set up. We set them up on purpose. So y'all see what way this thing's going to work. What we're going to do is we're going to take all the puzzles down and we're going to put them all under the table. So at the end of the day, class will be cleaned up there, but and y'all see where the wire got, where the jumper cables go. They're on the wire. Take these things off, you take these wing nuts off, on these wing nuts on the table, put them on the disconnect. Okay. All the bottom where your storage modules at, there's tables at the bottom, and that's everybody's cleaned up with there. In the first place to look for is back there on the table in the center. If you got an extra part, you put it on that table. Okay, so where somebody will be in this guy over here don't need to come from somebody else. We'll find it on it's not on your table, we'll find it on the pieces. It's not you. So that's station number 2. We go down this side over here. Oh, this side, this station is pretty y'all can use it. 2 people working. I know. Of course, I think these ones are you. If I don't, don't do 2. One's empty, so they start with 2. No, we're working two to a team, Kerry. What? That's okay. I'll run off some for today's class. That's the wrong form. Look at what it says at the top. What does it say at the top?